The oxidation states mainly depends on the number of electrons in outermost shell or the number of electrons in the penultimate shell. D0 or half-filled or completely filled electronic configurations will be having the highest stability in their order. When the N is increases, N is nothing but number of unpaired electrons, then the magnetic moment will be usually increased. Hello everyone. This is Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. Now, I am going to start session 2 from the chapter D and F block elements. In the previous session, we have discussed about introduction of D and F block elements, general characteristics of transition elements, general electronic configuration of transition elements and trends in properties in that atomic radii, ionic radii, density, some of the other characteristics also we have discussed. So now we will continue trends in properties of transition metals of first series. In the oxidation states, we will discuss now. All these elements except the last member exhibit variable oxidation states. All these elements being metals give only positive oxidation states. Except last row or except last member means which is the last member in the first transition series, zinc. It will not show any oxidation state, but remaining the previous one in the first series will show almost variable oxidation states. Since they are considered as metals, it will show only positive oxidation states. The reason for giving different oxidation states is as follows. The energy difference between the 4s electrons and 3d electrons is small. Energy difference between 3d electrons and 4s electrons is little bit small. So, hence 3d electrons require little energy to get promoted to the valence shell. Since the energy difference between 3d and 4s is very small, 3d level or electrons will require only little amount of energy to get promoted for or to jump into the valence shell. As such, they can be easily promoted to the valence shell, therefore they are also involved in bonding. Due to this small energy, due to the promotion of that 3d to 4s, so they will involve in bonding also. The oxidation states of these elements depends on number of electrons present in outermost shell, that is Ns or 4s, number of unpaired electrons in 3d orbitals of penultimate shell. The oxidation states mainly depends on the number of electrons in outermost shell or the number of electrons in the penultimate shell. The minimum oxidation state is given when only 4s electrons are involved in bonding. When it will be considered or when the minimum oxidation state will be given when the 4s electrons involved in bonding, while the maximum oxidation state is given when all 4 electrons and all unpaired electrons in 3d are involved. Minimum oxidation state only 4s electrons when involved in bonding, maximum oxidation states when 3d all electrons and 4s electrons will be involved in bonding. Hence minimum oxidation state number of electrons in 4s, maximum oxidation state number of unpaired electrons in 3ds and number of electrons in 4s. Now all these elements contain 2 elements in 4s and hence they all give a common minimum oxidation state of +2 except chromium and copper, which have minimum oxidation state is +1. Except chromium and copper, all will show +2 and chromium and copper will show only +1 oxidation state. See here, scandium +3, titanium +2, +3, +4, vanadium +2, +3, +4, +5, chromium +2 to +6, manganese +2 to +7, iron +2 to +6 except +5, cobalt +2, +3, +4, nickel +2, +3, +4, copper +1 and +2, zinc +2. Manganese is the element which has the highest oxidation state till +7. See here, involvement of 3d and 4s electrons. The relative stabilities of various oxidation states of a given element can be explained on the basis of rule of extra stability, according to which D0, D5, D10 configurations are stable configuration. As I told in the previous session, D0 or half-filled or completely filled electronic configurations will be having the highest stability in their order. or stable configuration. Hence, the ions which have these configurations are more stable. For example, the stability order of some ions, titanium with +4 oxidation, 3D0, 4S0 is more stable than titanium +3 because 3D1 is there. Manganese +2 is more stable because here half-filled d orbital can be seen rather than Mn, that is manganese +3, here 3D4. Iron +3, Fe3 plus half-filled, this is 4S0, Fe2 plus 3D6 and 4S0. When 3D0, 3D5, 3D10, it is having more stable electronic configuration, that is relative stability of oxidation state. Next trend, that is magnetic properties. The paramagnetic nature is due to the presence of unpaired electrons. Whenever the unpaired electrons will be present, those properties will be called it as magnetic properties or paramagnetic nature. So that unpaired electrons will be calculated by the magnetic moment mu of an element or ion is given as mu equal to root of n into n plus 1. This is Bm, the unit Bohr magneton. And n is nothing but number of unpaired electrons present. In that electronic configuration, the number of unpaired electrons will be considered as small n. Thus, the magnetic moment increases with the increase in number of unpaired electrons. When the n is increases, n is nothing but number of unpaired electrons, then the magnetic moment will be usually increase. Hence, the observed magnetic moment is useful to know the number of unpaired electrons present in an atom or ion. In the first transition series, as the atomic number increases from 21 to 25, the number of unpaired electrons in 3D series increases from 1 to 5 and hence the magnetic moment or paramagnetic character increases and becomes maximum at manganese. Since the atomic number 21 to 25, it is having number of unpaired electrons and will show usually paramagnetic nature and magnetic moment will be increased from 21 to 25 and maximum at manganese having atomic number 25. However, thereafter the number of unpaired electrons decreases with the increase in atomic number, as such the paramagnetic character decreases. From 21 to 25, unpaired electrons will be increased, magnetic moment will be increased. After 25, the unpaired electrons will be decreased since the atomic number will be more. So, the Bohr magneton or the magnetic moment will be decreased. By that reason, in between, manganese, which is having atomic number 25, is having the most magnetic moment in the series. At zinc 3D10, the number of unpaired electrons is 0 and hence zinc is diamagnetic in nature. Zinc, which is a last element in first 3D series, it doesn't have any unpaired electron in its shell. So, it will be considered as diamagnetic in nature and it doesn't show the magnetic property at all. See how to calculate the magnetic moment by using root n into n plus 2 formula. So, cobalt 2 plus, cobalt having atomic number 27. So, if we take the outermost 7, that is 3D and 4s shell, 1, 2, 3, 4, 5, 6, 7 and later 4s. Okay, in 3D 5 orbitals only, in each orbital 2 electrons. See how it will be filled and remaining 3 unpaired electrons. These are all paired and these are unpaired here in the excited state. Cobalt 2 plus means 2 electrons will be removed. So, here no electrons, remaining unpaired electrons only 3. So, n equal to 3. Here number of unpaired electrons is n equal to 3, magnetic moment mu equal to root of n into n plus 2. So, root of 3 into 3 plus 2 Bm root 15. Root 15 equal to 3.87 Bohr magneton. The value of magnetic moment of cobalt 2 plus is 3.87 Bm. Next, we will take another example, Fe2 plus. For iron, atomic number is 26. Electronic configuration here 2 plus means 2 electrons will be removed and here the 4 unpaired electrons are present. So, n equal to 4. We have to amplify in that formula, n equal to 4. So, 4 into 4 plus 2 root 24. So, root 24 equal into 4.90 Bm and the value of magnetic moment of Fe2 plus is 4.90 Bm. Okay, this is how the calculation of magnetic moment in the element. Next is formation of colored compounds. We have already told the general characteristics of 3D elements. it can show the property of formation of colored compounds. Most of the compounds of transition metals are colored in solid state or in solution. The color of a compound is due to the property of absorption of light of certain wavelength from the region of visible part. Why it will show the color in that compounds only means because it will absorb light in the wavelength or in the spectrum region called visible light region. It is having the wavelength called 400 nanometer to 700 nanometer, which is a visible part. It will absorb that much amount or that much wavelength light. So it will show or it will reflect to the light of electromagnetic spectrum. The actual color of the substance depends on the wavelength or color which absorbs from white light. The color of the transmitted or reflected light is the color of the substance. It is complementary of the color which absorbed by the substance. See, with the elements with variable oxidation states, it will show the different colors. Okay, titanium, vanadium, chromium. Vanadium in 4 variable oxidation state, in chromium with 3 oxidation state, in manganese the least and the highest, iron also +2 and +3, cobalt +2, nickel +2 and copper +2. In which oxidation state, in what element will show the which color you can observe here, and it is mainly depend on the absorption of wavelength of certain 400 nanometer to 700 nanometer of electromagnetic spectrum, and it shows the visible part, and that part of nanometer will be absorbed by the element, so it will show the colored property by the element. Transition metal ions containing unpaired electrons or vacant d orbitals are therefore colored, which is having the unpaired electrons in the metal, so it will absorb the light or it will absorb wavelength and it will show the colored nature. Naturally, the transition metal ions which have completely filled d orbitals that doesn't have unpaired electrons are colorless. Which is having completely filled electrons, it doesn't show the colored property, which is having only unpaired electrons in their orbital, in the d orbital which show only the coloring property. The ions which have completely filled d orbitals, that is 3d10, are colorless. Example, zinc and copper. Zinc and copper completely colorless because it is having the complete electronic configuration. Cuprous ion has 3d10 configuration, hence it is colorless. Cupric ion Cu2+ has 3d9 configuration and contains one unpaired electron. As such, it is colored, that is blue. In 3d9 configuration, one electron will be less, one electron will be unpaired, so it will show blue color. When cuprous plus, that is Cu plus 3d10 configuration, no unpaired electron, it will not show any color. Hence, cupric salts are blue in color, while cuprous salts are colorless or white. Here you have to understand that whenever unpaired electrons are present, they will show color. Whenever no unpaired electrons in the element or electronic configuration, they will not show color, or it may be white. See here, scandium 3d0, number of unpaired electrons are 0, colorless. Titanium 4+, 0, no unpaired electron, colorless. Titanium +3, 3d1, 1 electron, unpaired electron, purple. Vanadium +3, 3d2, 2 unpaired electron, green. Chromium 3+, 3d3, 3 unpaired electrons, violet. Manganese +3, 3d4, +4, violet. Manganese +2, 3d5, 5 unpaired electrons, light pink. Iron +2, 3d6, 4 unpaired electrons, green. Fe3+, 3d5, 5 unpaired electrons, yellow. Cobalt 2+, 3d7, 3 unpaired electrons, pink. Nickel 2+, 3d8, 2 unpaired electrons, green. Copper 2+, 3d9, 1 unpaired electrons, blue. Again, copper +3d10, no unpaired electron, colorless. Even zinc 2+, 3d10, no unpaired electrons, colorless. In the single element with the variable oxidation state, whenever it is having unpaired electrons, it will show color. With element with also variable oxidation state, if it is no unpaired electrons like this, it will show colorless property. Next, catalytic property. I have told already the catalyst is which enhance the rate of reaction, and so many catalysts are present in D block elements. So most of the transition metals and their compounds have good catalytic properties. Their catalytic properties are considered to be due to the following reasons. On what concept? D block elements are having catalytic properties. According to modern theory of catalysis, the catalyst forms an intermediate unstable compound with reactant. According to modern theory of catalysis, the catalyst should form the intermediate state with reactant. Then that catalyst have a good property to enhance the reaction. This intermediate compound readily decomposes to give product and catalyst is regenerated. And after intermediate state, which is the intermediate state is a unstable product, unstable molecule, and it has to decomposes into product and catalyst is regenerated. So this is a major property which should be exhibited by the element, and that element will be then considered as catalyst. On account of their variable oxidation states, the transition metals form unstable intermediate compound readily. Due to the D block having variable oxidation state, it will carry the unstable intermediate state very easily. So it will be having a catalytic property in a good manner. These elements can also provide large surface area for the reactants to be observed side by side. This helps the reaction to occur on the surface of the catalyst. And these elements will give the large surface area to get attracted from the or to get reacted from the reactant. So the reaction will occur on the surface of the catalyst also. These are the two major reasons which show the properties by the transition elements, and it will be projected like D block elements will be having good catalytic properties. For example, iron in Haber's process for the manufacture of ammonia. In the manufacture of ammonia, iron will be used as catalyst. Nickel in hydrogenation of oils and unsaturated hydrocarbons. And vanadium pentoxide in the oxidation of sulfur dioxide to sulfur trioxide in the manufacture of sulfuric acid by contact process. In these major three processes, the elements from D block series you can be observed as catalyst. Next, formation of interstitial compounds. How it could be form interstitial compounds means interstitial compounds are those which are formed when small amounts like hydrogen, carbon or nitrogen are trapped inside the crystal of transition metals. In this metal, if you see, these are the metallic crystals and hydrogen, carbon, nitrogen are trapped in between. They are the capacity to found or hold the elements or atoms in between here. You can observe here hydrogen, carbon and nitrogen could be trapped inside the interstitial compound. After the trapping of these elements only, the interstitial compounds can be formed. This is the trend in properties of transition metal by formation of interstitial compound. Next, they are non-stoichiometric and are neither typically ionic or covalent. Ionic compounds already know they are hard in nature. The covalent property also you know. They are non-stoichiometric. After the formation of interstitial compounds, there will be no stoichiometry in that. These interstitial compounds have similar chemical properties as the parent metals but differ appreciable in their physical properties such as density, melting point, hardness, etc. After the formation of interstitial compounds, its density, melting point, hardness will also get changed, which is a type of physical property. Interstitial compounds are hard and denser. This is because the smaller atoms of lighter elements occupy the interstices in the lattice, leading to more closely packed structure. Due to the greater electronic interactions, the strength of the metallic bond also increases. Here, due to the elements which have been trapped in the compounds or metals, those trapped atoms will also give the density to the elements and the electronic interactions will also greater because no vacancy in between, only spaces. So its density and as well as it will become more harder than the before. They retain metallic conductivity and it will be having the metallic conductivity also. They retain its metallic conductivity. Examples: titanium, carbon here, iron, hydrogen, and these are the various interstitial compounds. Next, alloy formation. Transition metals form a large number of alloys. Alloys are formed by the metals whose atomic radii are similar. When the atomic radii is similar, it will form a large number of alloys. 3D series elements are quite similar in atomic size and other characteristics. Hence, the atoms of one metal can substitute the atoms of other metal in the crystal lattice. Thus, on cooling the molten mixture of two or more transition metals, solid alloys are formed. Okay, 3D series elements are quite similar in atomic size and other characteristics. Hence, atoms will be one metal can substitute the atoms of another metal. Thus, the formation of alloy can be expected. On cooling the molten mixture of two or more transition metals, solid alloys are formed after the cooling. For example, chromium, vanadium, manganese, nickel, etc. are used with iron to form variety of steels and stainless steels. With the iron, these metals will be used to form alloy. The alloy brass, copper and zinc, and bronze, copper and tin considerable importance here. These are the alloys. How alloy will be formed? When the metals will be having similar atomic radii and atomic size, then the one atom of metal can be substituted by another atom of having similar atomic radii. Metal can be substituted, then it will be cool the molten mixture of atom or metal, then will be alloy can be formed. These are the trends in or properties of D block elements in the periodic table. So, in the next session, we will discuss about some of the important compounds like potassium chromate and potassium permanganate, its preparation, its reactivity and its importance. I hope you have completely understood whatever I have taught today. We will meet in the next session. Thank you.